this is first digital functional testing, and it's mostly the same slides as 431 with a few changes to it. And just to remind you that a digital functional test is if you give it the input 0, 1, 0, give a digital circuit the input 0, 1, 0, and you're supposed to get a 0 out, but you get a 1 out, that's a functional error. So where you expect to get a 0, you get a 1, or where you expect to get a 1, you get a 0, that's a functional error. And let's see, the models that we're going to look at, we're actually only going to look at stuck-at faults. But once you look at how stuck-at faults are found, you can expand it out to bridging faults and stuck-open faults. And stuck-open faults means there's a floating wire because there's a break in the wire. And that can happen from electromigration, where current pulls the wire apart, or where heating and cooling with the expansion coefficients are different for different, like metal layers and silicon layers maybe expand at different rates, and it causes a crack in a wire or something like that. Bridging faults are when the signal lines are shorted together. So if you have an AND gate where the input is A and B, and those wires are shorted together, you'll always get the inputs will both be the same value. So if it's an AND gate, it'll act just like a buffer, really. And if it's an AND gate, it will invert whatever is stuck on the signal, or whatever the signals are. Okay, that was not a great explanation, but on to next. And again, we're going to be looking at these stuck-at faults right here. And let's look for single block testing. So for the single block testing, the simplest digital circuit is a gate. And just looking at an AND gate as an example, if I give an AND gate a 1 and a 1 on its input, you expect a 1 on its output. But if it has a 0 on the output, then the output has a stuck-at-0 fault. In the same way, if you give an AND gate a 0 and a 1, you should get a 0 out. But if you get a 1 out, now you have a stuck-at-1 fault on the output. So stuck-at-0 means there should be a 1 on the wire, but there's actually a 0. And a stuck-at-1 fault is where you should have a did I say that backwards? You should have, for stuck-at-0, you should have a 1 on the wire, but you have a 0. And for a stuck-at-1 fault, you should have a 0, but you have a 1. Okay, and that can happen just some impurities. For example, some dust can fall and short 2 wires. Now the output's shorted to ground. Some other if you have a break in the let's say from this PMOS to the output, then the NMOS will pull it down. There's nothing ever pulling it up, so this will stay low. You can have shorts, just like you had over here. You can have shorts between the output and ground, or output and supply. And those all cause a node to never change from a value, either stay at 0 or stay at 1. Okay, so a test vector is an input you give a digital circuit to test if it's working correctly. So for example, if you wanted to test for a stuck-at-0 fault on the output, you would put 1, 1 here. That should give you a 1 on the output, but if you get a 0 here, then you know you have a stuck-at-0 fault on the output. Okay, so whatever node you're looking at, if you're looking at a stuck-at-0 fault on the output, you try to put a 1 on it. So if it's a stuck-at-0, you try to put a 1. If you're looking at a stuck-at-1, then you try to put a 0 on that node. Okay. This is kind of jumping back, but when you have a fabricated IC with a closed lid package, the only way to test it is through the pins. You have to put some inputs on the pins, and then you have to watch the output on some other pins. You can't like crack the IC open and start probing the insides. You just can't do that anymore. So testing is hard. If you have a lot of signals to test, you can't put them all out to pins on the chip, or else you'll have a really large package and tons of pins, and the pins will only be used for testing, and then you've wasted a lot of resources and probably using a more expensive package. So these are if you have access to as many inputs as you need and access to the output. So we already kind of did this one, but if you're looking at a stuck at 1 fault on the output, what value do you try to put on the output? And if you said 0, that's right. So you try to put a 0 there, and if it's a 1, then you have a stuck at 1 fault on the output. So, and then there's to put a 0 on the output, there's a whole bunch of different things you can do. You can put 0, 0. You can put 0, 1. You can put 1, 0. So there's 3 different inputs you can give, but 0, 0 also works. Stuck-out faults often happen at boundaries, like where an interconnect connects to a gate, or where a pin from the package connects to a wire, or where the output of a gate connects to a wire, or where a wire connects to a pin. So at pins, at boundaries, like where a wire hits a gate or where a pin hits a wire, that's where you see the most stuck-out faults. And if I put in a stuck-out fault at each one of those weak spots, I end up with a total of 12 possible faults. Okay, so if you have to test all 12 faults for every gate, that means that if you have a 600,000 gate design, you multiply that by 12, and that's how many tests you have to do. So that is not efficient, and so you try to find a more efficient way to test it, and that's what we're going to look at next. So if I have a stuck at 0 fault here, that's the same as having a stuck at 0 fault here. Either way, I'd put a 1 on this wire. So it doesn't matter whether the fault's here or here. So on any single wire, we generally only put one spot where the faults are, and we get rid of anything else. If you notice before, we had a stuck at 0 fault here and a stuck at 0 fault here to test for. There's a possibility of a stuck at 0 fault happening here or here. But again, if I'm testing for a stuck at 0 fault here, I put a 1 on here, and that's the same value I'd put on for a stuck at 0 fault here or a stuck at 0 fault here. So I might as well not get rid of any duplicated tests on a wire. That's what I've done here. And we started out with 12, and the birds should be asleep now. But now we have it down to 6 faults. Right, so let's look at that. If I'm looking at stuck at 0 fault on A, I need to put a 1 on here, and I need to put a value on B, which will tell me if A is wrong. And the only value you can put on B that will tell you if A is wrong, if you can only let's say it's a little better. So to test this AND gate completely, I can give it inputs and I can watch the output. That's all I have. I can't probe anything inside the gate. I can just give it inputs and see if the output's wrong. So to do that, if I'm trying to check for a stuck at 0 fault here, I have to put a 1 on here, because we're trying to see if this just never goes to that sticks at 0 and never goes to 1. So I try to put a 1 on there. If it fails and stays at 0, then I have a stuck at 0 fault. But to pass that through, if I have a 0 on B, I'm always going to get out equals 0 no matter what, whether A is stuck at 0 or stuck at 1 or working correctly. So what I want to do is, if I want to test A, I need to put 1 on B. And then if A is 0, I'll get a 0 out. If A is 1, I'll get a 1 out. So for an AND gate, I have to put the other input as 1 in order to pass the information through whether this wire has failed or not. So if I'm testing for a stuck at 0 fault at A, I need to put 1 on B so the A value will get passed through. And if it's correct, I'll get a 1 on the output. And if there's a fault, then I'll get a 0 on the output. If I have a stuck at 1 at A, now I need to put 0 on A and 1 on B. Again, if I had 0 on B, I'd always get 0 for my output, and it wouldn't tell me if there's a fault on A. And then I'd get 0 if it's working correctly, 1 if it's working wrong. Same thing for the B input. Stuck at 0, stuck at 1, but now it's B that I'm either set to 1 or 0. On the output, if I want to test for a stuck at 0 at the output, I need to put a 1 on the output, and the only way to get a 1 on the output of an AND gate is to have both A and B equals 1. And if both A and B are 1 and the AND gate is working correctly, then I get a 1 on the output, a 0 if it's bad. All right, it's already 11 minutes in. Okay. For a stuck at 1, then you need a 0 on your output, and again, there's 3 possible inputs you can give an AND gate to put 0 on the output, and that's 0, 0, 0, 1, and 1, 0. Okay. Next thing to do is say, well, now I have 2, 4, 6, I have 8 tests. I have 8 tests here, but let's see if I can do 2 at the same time. So let's look at this. For a stuck at 0 at A, if A is 1, is B is 1, and B is 1, and then I see if the output is 1 or 0. Let's see if that does some other tests. And it turns out for a stuck at 0 at B, it's the same input and the same output you look for. And you really don't, if you have an IC that has a fault, you really don't care where the fault is. You can't fix it. And eventually you have to go debug it and all that. But for a finished product, you really don't care where the fault is. You just care if there is a fault. So all 3 of these, this checks for a stuck at 0 at A, this checks for a stuck at 0 at B, and this checks for a stuck at 0 on the output. So any one of these tests for all 3 of these stuck at faults. So this test right here, you do this, you give it A and B equals 1 and see if the output equals 1. But you only need to do it one time because you've already done this test and this test if you do that test. So what that says is for a stuck at 0 fault, you can either test here, here, or here, because it's the same input and the same output you're looking for. You're actually doing all 3 tests at the same time. Okay, then let's look at this one, and just so happens that this is the same test, so you only have to do one of those. And then this and this, that's the same test. So you only need to do one of those. So you only need to do one of the reds, one of the greens, and one of the blues. And notice that you've already done a stuck at 1 fault test at your output. So this would just be a redundant test. If you did one of these tests, then this would just be a redundant test because you're checking if you get a 0 at the output or 1 at the output. And these both do that for you. So now you have the red test, the green test, and the blue test. So it turns out you can completely test an AND gate with just 3 tests. And that's 111, 010, and 100. And this can be done in any, you can consider this test as being done on A or B or output. It covers the stuck at zero fault at A, B, and output. Right? So here's a question for you, and because this video got long, what, again, for an OR gate, you can reduce the number of tests. How many tests can you completely test an OR gate with? And if you have a test that does multiple tests, if you have an input that does multiple tests, then for that input, you can check off all of the tests that input covers. So I'll give you the answer at the beginning of the next video.